in classical mechanics, we know the following equation of motion. For an observable. So if we have phase space that's a 2. If you have phase space r to the 2n and you have coordinates q's and p's for this phase space, then an observable in classical mechanics is a function. And the time development of this observable, if you like the Heisenberg picture dynamics, is determined by this equation of motion, where h is the Hamilton function, Hamiltonian. I think I have a minus sign error here. So dq dt, dh dp, right? I think there's a minus sign there. It doesn't matter for what I'm going to say. So you could think of h, I mean, if you look at this, h is the generator. You think of h as the generator of time translations. So that's a symmetry. And the symmetry group is isomorphic just to R, translating backwards and forwards in time. And you think of H as the conserved charge as well, so that's another interpretation. Now, in quantum field theory, you proved this theorem relatively early on, the so-called Noether theorem, that associated to any continuous symmetry, there's a conserved charge. And what you don't prove, and in fact is left unexplained in most textbooks, is what you might call inverse Noether theorem, that if you know the conserved charges, then you can build up the symmetries, because these conserved charges are, in fact, the generators of the associated continuous symmetries. And in the classical world, nothing's different. In fact, the Noether theorem is classical. So usually we implement these statements in the quantum world where we've promoted our observables f and h to operators. But of course, the origins for all these things is in this classical setting. So if you think about h and Hamilton dynamics really as just one generator of a continuous symmetry, then it's sort of natural to think, well, what happens if I have a bigger symmetry group? So the kinds of symmetries that you expect in, say, relativistic physics is the group G is no longer just time translations, but you get space-time translations. So you can translate on space and time. And also you can do rotations in space. And you can also do Lorentz transformations. So the kinds of things you end up with in special relativity, for example, the kinds of groups that you find, are things like this, O3-1 semi-direct product R4. It's the group, the Poincaré group. And associated to each of this is a continuous symmetry group, and there's a generator associated to each of the possible infinitesimal transformations. There's a Lie algebra for this Lie group. So associated to each generator, there's a corresponding conserved charge Q. And this inverse Noether theorem, which I won't ever really write out, but just say in words, says that all these transformations, as implemented on your physical system, will be generated by these list of generators here, Qj. So each of these are like a Hamiltonian, right? The Hamiltonian is indeed one of these Qj's. So Q naught is H. Typically, when we have the Lorentz group, not the, the Lorentz group, then we bundle together all these conserved charges in something called the energy momentum tensor, which is a symmetric 4x4 matrix of conserved charges. And the 0, 0 entry, so I'll write it 0, 0, is actually H, the energy. So J, comma K, but so, we don't want to sort of tie this too strongly to relativistic physics, so I'll just write it like this. So these list of conserved charges may or may not form a vector or a tensor or whatever. It's just a list of conserved charges that generate the symmetries. And this thing that I'm calling the moment map that I haven't yet introduced, what is it? Well, it's just the vector of these generators. So in physics terms, I've already finished the discussion. So I will just write that out in words, and then we'll see how to implement that using the framework we've been working on for the past couple of weeks. I'll summarize a couple of these things. So the generators act on the observables, which are just functions on phase space, just according to this standard Poisson bracket symmetry group. So what is the moment map? Well, the moment map is just the list of these generators. There's nothing more, nothing less. So it's like a vector. you think of the moment map as kind of like the generalized Hamiltonian. I mean, I think the best analogy is with quantum field theory, where you think of the moment map more as like the energy momentum tensor. It's the structure that allows you to work out a general symmetry transformation for, say, the Poincare group or whatever group that you like. Now, we're going to attack this problem of incorporating these ideas into our framework in sort of two ways. The first is, well, we could have left it at this stage, right? Just in terms of phase space, everything is pretty fine. We didn't need to invoke symplectic geometry and all that machinery to fully discuss this stuff. Could have left this at canonical transformations. However, it's nice to think that we could generalize these ideas to the more the larger setting of symplectic manifolds. So that's what we're going to do. We're going to try and interpret these statements in terms of symplectic manifolds. And then we'll see that we actually have some problems in being able to write out, say, this equation here. And then we'll study some examples. But at the physical level, what we're doing is building, if you like, generalized energy momentum tensors for symplectic manifolds. But before we do that, we have to spend a little bit of time thinking about Lie groups, just building up enough understanding of these words here in a slightly more precise setting. And that will require us to talk about a little bit more Lie group theory, in particular adjoint and coadjoint representations. Yesterday we talked about Lie groups, and today we're going to talk further about Lie groups. I mean, obviously the important object when trying to generalize Hamiltonian dynamics to include other symmetries. So as you recall from yesterday, Lie groups are these smooth manifolds that have a product operation and an inverse operation that are also smooth. So this is extremely natural if you think of smooth manifolds in groups and how would you put them together. And then once you've got this multiplication structure, then it allows you to get all kinds of consequences in a canonical way. So you can find a canonical action of a Lie group on itself from the left and from the right. Well, it turns out there's a third action, which is basically both of them, which is also canonical in some way. So the Lie group acts on itself by left multiplication, by right multiplication, but also via conjugation. So let's explore conjugation for a little bit. So that means that every element of the group gives rise to a diffeomorphism of the group itself. And that diffeomorphism is defined, well, we write the diffeomorphism as psi g. And the way that psi g acts is that it takes an element of the group and it gives you g times by a times by g inverse. So conjugation. Take any element of the Lie group and conjugate it by the element g. Because this is a sequence of multiplications and inverse maps, it's a smooth map, so it's a diffeomorphism, an invertible map. So it's a diffeomorphism. So of the group takes the element of the group to itself. So we can study what it does to vector fields as well. So if you have any map on a manifold, you can see what it does to your vector fields. And since we know that vector fields on Lie groups, left invariant vector fields, are the same as understanding the tangent space at the identity, we can just think about what happens at the identity of this map. And what this does is if you take the derivative at the identity of the Lie group of this conjugation map, psi, then you get a map on left invariant vector fields. So the left invariant vector fields is this Lie algebra. This map is furthermore invertible. And we give this map a name. It's called add G and it goes from left invariant vector fields to left invariant vector fields. Adjoint action, adjoint representation of the Lie group on the Lie algebra. Pretty neat, right? Just for doing no work at all, you get actual bona fide representations of the Lie group. So for matrix groups, we can write things out a bit more explicitly. So show that for matrix groups, if you take the adjoint action of some element of the matrix group, which you can always write as an exponential, we proved that yesterday, acting on some left invariant vector field, and that's none other, at t equals 0, that's none other than straight out commutator for all x and y. So I guess I'll do, that's an exercise, not an example. So one group that's very interesting to look at in the context of classical mechanics is the rotation group, SO3. And elements of SO3, well, what are they? They're symmetric 3x3 matrices. So write it as O. An element of So an element of SO3 is a 3 by 3 matrix that's orthogonal and it has a determinant equal to 1. Then the Lie algebra for SO3 is the set of skew symmetric, I'll put it in GL I guess, skew symmetric 3 by 3 real matrices that are invertible such that, well, that's it. And there's only 3 such matrices, right? So an arbitrary skew symmetric 3 by 3 matrix looks like this. So you can identify, it takes 3 numbers, you can actually identify it with R3.
What do you mean by in the brackets, the GL, why is this G like the Lie algebra G?
This is, what's this thing here? This is the Lie algebra of the group GL. General linear group, yeah. Okay. Yeah, I'm. Like that's, yeah. I think that's absolutely causes no harm if we just say M3 of R. Cause, yes. Right, so that's what the left invariant vector fields look like on SO3. Okay, this is also a bit of an exercise, you have to work that out. And that comes from thinking about the tangent space to the orthogonal group. So we had this vitally important exercise yesterday. If you think about the tangent space at the identity of a Lie group, then that's equivalent or is isomorphic to the left invariant vector fields on the Lie group. And so the tangent space to SO3, you can find that by looking at these conditions here. So these show that SO3 are an embedded manifold in R9. So it takes 9 numbers to specify a 3 by 3 matrix. And here we have 9 conditions on this matrix, 9 equations. And SO3 is the result of applying these conditions. So you can think of SO3 as a submanifold of R9, and then you can work out the tangent space there, and then if you work through all these equations, these turn into linear constraints on the tangent vectors, which are none other than those constraints there. And then this tells us what the Lie algebra is. It's this set of this 3-dimensional space of skew symmetric matrices, and then you can then apply this formula here to study the adjoint action of the orthogonal group on itself. We'll say a bit more about that before the end of the lecture. Yeah?
Question. So this bracket up there is to be understood as the Lie bracket of vector fields, or?
Oh, okay, right. So the question is, how are we to understand this bracket up here? This is actually the commutator of matrices. See, this is a matrix. This is a matrix. So.
Are we implicitly using like the canonical basis in some way?
Are we implicitly using the canonical basis? I don't. This is a basis independent expression, so.
Yeah, but this is like a. This is not an algebraic expression in the first place, I think.
The thing on the right is algebraic.
Yes, but on the left it's not.
Why not? I mean, well, okay. I mean, that's. You take. This is an element of the Lie group.
Yes.
So it's a 3x3 matrix.
Yeah, but it's a 3x3 matrix when we specify coordinates. That's what I mean.
Specify coordinates.
Yes,
I don't know what that sentence means, I think.
Like, we can arbitrarily change the entries of the matrix by changing coordinates. And kind of, I think my question is this commutator of matrices invariant under these changes? Or not?
Yeah, absolutely right. So this expression here is basis independent. It's just the product in the group, AXY minus YX.
Okay, okay.
Yeah, a bit, okay, so. So we've put a ring structure on the group.
Yes.
But that's basis independent as well.
Yeah, I think it kind of makes sense, but I think it's just the implicit, the implicity of this equation. Where on the left, there's a different interpretation as on the right. I think that's.
On the left, there's a different interpretation than on the right. So this is, I don't think so. I honestly don't think so. So here, this thing here, what is this? Well, that's something that looks like G, Y, G inverse. And then these G's depend on some parameter T, and then you differentiate them. So so that's something inside the Lie group. And that's a vector field on the Lie group, a vector in the tangent space to the identity, as is this thing here. Remember, an element of the tangent space is a Lie algebra, which is a vector space with an associative product. So I think it all works out.
Okay.
Y is in the Lie algebra, right? Sorry, commutator elements of the Lie algebra. And so you can take a representation, and then these will be the standard matrix commutator.
I think this also holds for if we have some abstract Lie group and not a matrix group.
Right, yeah. Exactly, yeah.
There's no, like, yeah, then the commutator wouldn't be like a matrix commutator.
But when you take a representation, it is.
Yeah. But in general, it's the commutator of identified by the left invariant vector fields.
Yeah.
Coming from the left invariant vector fields.
Yeah.
So wherever you have something acting on a tangent space, you can take the cotangent space and see what happens. So there's a natural pairing between G and its joule. Let's call that angle bracket, comma. And it goes from, it takes two arguments, one from the joule, one from G itself, and gives a real number. And it's none other than that action. Just take the element of the joule and feed it the element of the Lie algebra, and it gives you a number. And whenever you have such a pairing, you can find the adjoint under this bilinear form of anything that happens on the right-hand side. So that's what we're going to do now. So if we have ourselves something in the joule of the Lie algebra, and then we act on it by this adjoint map here, then we can also use this pairing here to have a equivalent action on the joule. Oops, inverse. And you want the inverse down here so that compositions work out nicely. When we compose, as we'll see, we can compose two adjoint transformations and get a second one. And then we want that this co-adjoint representation behaves like a representation. So we need the inverse down here. And that's got to be true for all x and for all xi. And we give this thing a name. So this collection of maps add G star forms also a representation of the Lie group. It's called the coadjoint representation. So we got these, I've said the word representation 2 or 3 times now. Is it a representation? You have to actually show that. Oh gosh, yeah, sorry. It has to be add star without the G, that's right. Yeah. So we want that they're representations, so that's your job. You have to show that they behave nicely under composition and under inverses as well. So now we can get to the topic of this moment map. So let's go back to our more general setting. We no longer work with just phase space, we work with a symplectic manifold. So we go back to this general setting where we've taken phase space and replaced it with a symplectic manifold, and we're letting G be some Lie group acting on M via symplectomorphisms. So it's got a smooth action. And I put connected in brackets because funny things can happen if you have disconnected groups. We'll maybe say something about that. So for every x in G, so every left invariant vector field on the Lie group, we get a corresponding vector field on our manifold. Hope that's clear how that works. I guess I'll say some comment on that. So X inside G, we can form the flow. This generates a one parameter subgroup of the Lie group. So we can form these guys here, xt of X. So this is a one parameter subgroup of the Lie group G. And then the smooth G action on M gives us a one parameter family of maps on M. And then differentiating this one parameter family of maps gives us a vector field psi of X. So to every left invariant vector on the Lie group, we get a vector field psi X on M via this smooth action of G on the manifold M. Now, since G acts via symplectomorphisms, it's not just any old vector field that we get here. So each of these psi's is a symplectomorphism, so it's got to preserve the symplectic 2 form. So we learn that this vector field that we get on M from applying one of our left invariant vector fields from G, that's a symplectic vector field. And that means variously that the Lie derivative of the 2 form is 0, which equals the internal product of the 2 form. Oops, it certainly does not equal that. It equals that, which implies that the internal product of the 2 form is closed. So it's what we know about symplectic vector fields. Now what we're interested in is not these symplectic vector fields. Well, we are, and it's very elegant that you can understand Lie group actions on manifolds via the Lie algebra of symplectic vector fields. It's really nice, right? We get this homomorphism from the Lie group, from the Lie algebra G to the Lie algebra of symplectic vector fields. It's super cool. But we want something more. We always want more. You always want more. And what you want this time is the answer to the following question: is this one form here exact? That would be great, right? Because then that would mean that, in particular, this vector field, the vector field implicitly defined by this one form here, the Hamilton vector field, that would imply that this vector field here, sorry, is Hamilton. Now, there's some bad news, right? You already knew the bad news from just Hamilton vector fields. It's not always possible. There can exist symplectic actions which are not giving rise to exact vector fields like this. And we already know some, right? Just take any manifold where the first cohomology group is non-trivial, and then you know that there must be symplectic action of, say, the circle group on that manifold which isn't exact. I think the simplest example we had was like the circle acting on the circle or something like that. So, bummer, right? You don't get to have what you really want. But what we can do is at least spell out what we do want in terms of some conditions. And there's some obstructions to getting that this vector field psi is Hamiltonian. And we'll spell out those obstructions now. But before we do that, I think it's worth commenting that operationally, from a physical perspective, there's no harm in having symplectic actions that aren't giving rise to exact one forms like this. I mean, I think the physical interpretation is completely unharmed. Like, observables, you can still talk about observables, you can still talk about their dynamics. It's just you now have to operate with symplectomorphisms instead of Hamiltonian vector fields. And then it's more the notion of a conserved charge which gets challenged by symplectic actions. So, you can't write the Hamiltonian for this thing here. You can't write dH, which is maybe that's fine, right? You can't really ever measure directly H anyway. So you can't measure the Hamiltonian in physics. In quantum mechanics, you can only measure changes in energy. You can't measure H itself. And so changes in energy are like dH. So to some extent, are like that one form there. So to some extent, I think this is already a very satisfactory answer for how to generalize things to the classical, generalize Hamilton mechanics to a much more wider class of actions. And if you don't have a Hamiltonian interpretation, then fine, because operationally you can't measure those things anyway. But somehow we've never been really forced in physics to deal with that. We've always gotten away with Hamiltonians and other generators. So why not at least spell it out, these conditions that would guarantee that these one forms are actually exact? So if we write our smooth action, symplectic action as psi going from G to symplectomorphisms of M, then we come up with the following definition of what would be like the Hamiltonians corresponding to these symmetry groups. Or what would be a Hamiltonian action psi. This action has got nothing to do with the action in the principle of least action. This is just like a group action. It's a bit unfortunate that the word action is already taken in physics. So this action is a Hamiltonian action. Well, you guessed it, right? When's it Hamiltonian? Well, it's Hamiltonian when these one forms are all exact. But we have an extra condition that we have to lay on top. And it's kind of convenient to collect together all the... So I'll pause for a moment. Suppose these are all exact, right? So that would mean that that's dHx. There's some hx, some h that depends on x for all x in G. So I'll just pause from this definition. Just suppose that it is possible. Suppose that there's a miracle and our symplectic action really is like Hamilton for all x. Then that would mean that you can always write this one form here as d of h of some x, and h is some function. H is a function from the manifold to the real numbers. But, you know, why stop there? You could hope that this is actually a linear function of this argument x here. I think that's perfectly legitimate hope, that h of x plus y is h of x plus h of y. So h takes, if you like, at every point in the manifold, h gives you a real number, and that real number, how do you get it? You get it by putting in an element of the Lie algebra. So actually h is somehow an element of the dual Lie algebra at every point on the manifold. And so what we're going to do is capture that observation by introducing a map mu, which goes from the manifold to the dual Lie algebra at every point in the manifold. And the purpose of this map mu is to mimic this expected behavior here of this Hamiltonian that depends on the vector field x. So this action is a Hamiltonian action if there exists a nice map that goes from the manifold to the dual of the Lie algebra. But not just any old map will do. There's some conditions such that for each x in the Lie algebra, right, each vector field, each generator of a one-parameter subgroup of the Lie group, we let mu superscript x be the function that goes from M to R, where mu superscript x evaluated at a point on the manifold is none other than mu p comma x. So this really is our h of x. I've drawn it as superscript hash there and psi x there. Okay, I'm going to use two notations for exactly the same thing. All right, so let x hash be the vector field on M generated by this one parameter subgroup of G. And then it's a Hamilton. It's a nice Hamiltonian for all these different vector fields if you can write this one form here as an exact one form by d of h. So that's sort of condition one that we'd want an action to satisfy if it's Hamiltonian. But there's another condition. This one's a little bit less transparent, but has to do with what I said right at the beginning of the lecture today. So you would like that this Hamiltonians here, these mu of x's or h of x's, what I called before, you would like that these things are like the conserved charges of the symmetries and that they obey a Poisson algebra. That's exactly the Lie algebra that you expect from these generators to obey. Turns out that's not always possible, so you have to add an additional constraint. And the obstruction, again, is something global. So it turns out if you have like phase space, nice flat phase space from classical mechanics, it's always possible to arrange for these things to obey the correct Lie algebra under the Poisson bracket. But when you've got a globally non-trivial phase space, then it's not always possible. So you have to capture what it is that's going wrong and make it a condition. And that's what we're going to do in the second part of this definition. So this definition has two parts. The action is called Hamiltonian if there's like this generalized Hamiltonian map there, which is like a vector of numbers, such that condition 1 is true, and then there's a condition 2. And condition 2 has got to do with these generators obeying the right algebra. All right, there's the second condition that we need to obey to call this thing a Hamiltonian action. It says that if you do the action and then evaluate the moment map, that's the same as evaluating the moment map and then doing the action. It looks harmless enough and indeed is instantly satisfied whenever G is, say, a one-parameter group. The trickiness comes when G is not a one-parameter group. So for connected Lie groups, we get an equivalent definition. And that's the one that maps, is most closely related to how I introduced this topic at the beginning of the lecture. So connected Lie groups are probably the most natural ones to think of. I mean, for disconnected Lie groups, then there are problems. But for connected Lie groups, we'll see how these two conditions translate into the ones that I used to introduce this topic. So this is an exercise, equivalently, so it's an exercise. You just have to dualize everything you see here. So condition 1 becomes that this co-moment map, when evaluated on an element of this Lie algebra, is just this mu of x. It's just the Hamiltonian for x. And condition 2 is the one which I referred to as the inverse Noether theorem. If you evaluate this co-moment map on a commutator, then that becomes a Poisson bracket of these functions. So you can really think about these as generators of the symmetries on the observables of the system. And in fancy words, that turns phi star into a Lie algebra homomorphism where the Poisson bracket is the Lie bracket. So there you go. We've now got a reasonable working definition, note the word definition, for what a symplectic action, so for what a Hamiltonian action could be when the Lie group is not just S1 or the real numbers. For this to actually have any use whatsoever, it better be the case that there exist such Hamiltonian actions. I certainly haven't proved that yet. I've just given you a definition. These conditions may be so strong that they're only satisfied by Hamiltonian actions of S1. That could be the case. Of course, it's not the case. So let's show some examples to prove to you that it can be a useful concept, and actually that there exist non-trivial examples. So the first place we'll go looking for a non-trivial example is the simplest Lie group we know that isn't trivial, and that's SO3. Okay, there's all kinds of little miracles that happen when you have simple Lie groups. Here's one of them. So the Lie bracket on the Lie algebra of SO3 can be identified with the cross product on R3. So I'll show you how we do that. So firstly, to every element of the Lie algebra, which is a skew symmetric 3 by 3 matrix, we identify an element of R3 just by taking these three numbers here and stringing them out as a vector. So we identify elements of the Lie algebra with elements of R3. That's fine. We have a three-dimensional tangent space to SO3, so that was obviously going to work. But the minus signs here play a role in getting this right. So A underline just means the vector of three numbers. And if you take the commutator of two 3 by 3 skew symmetric matrices, the matrix commutator, then you can identify that if you work it out. Actually, it's a tedious computation of 9 entries. Some of them are 0. Well, evidently 3 are going to be 0, and the other 3 determined. So it's actually only 3 computations you have to do. You can identify that with the cross product of these two elements of R3. And there's some exercise. So the dual Lie algebra is also identified with R3. Then you can find out that the adjoint and co-adjoint actions on the Lie algebra are actually none other than the usual SO3 action on R3. So you want to show something like this, right? You want to understand how a skew symmetric. Suppose you have an infinitesimal rotation. I'm going to do this in purely physicist way right now. I'm not going to do this properly. You have an infinitesimal rotation like that. And then you look at the adjoint action on the element of the Lie algebra. And then you see that to first order you just get it back again, plus the second order you get this commutator. And that. And that you can write, identify with A plus epsilon B cross A, but that is the infinitesimal form of O as a 3×3 matrix acting on the vector A. Transpose. That's a highly elliptic argument, but maybe it's of some help to you. You could just do it properly. Okay, we're going to use this exercise in a minute. So the next example, we'll actually find the moment map associated to spatial translations. Should give us the standard momentum vector, and we'll also find the moment map for spatial rotations, which should give us the spatial part of the energy momentum tensor. And we're going to use this identification quite heavily throughout. So beware, whenever you see an A with an underline, that's going to mean, I'm going to be implicitly meaning I have that corresponding element of the Lie algebra of SO3. And I'm going to be meaning also at the same time, just for extra confusion value, an element of R3. So this is example 2. So usual phase space, 3-dimensional phase space, and we're going to take for our 2 form the standard 2 form. Okay, let's deal with our first abelian example. So we're going to take R3 to be our Lie group of symmetry transformations, and they're going to act by translation. So we know that there's a conserved quantity for each symmetry of translation. It's just the momentum in the three directions. So there should be a three vector of conserved quantities associated with this three-dimensional action there. So associated to every three vector in R3, so this is our group, we get a corresponding symplectomorphism psi A. And how does that symplectomorphism act? Well, you give it a point in the manifold R6, and it gives you back a point in the manifold R6. Namely, just translate by A. And we've done translation before. We know how to find the vector field corresponding to a translation. So if you have a vector, X is identified with A underline, remember? X is, that's Lie algebra, not the Lie group. So X is identified with A underline for an element of the Lie algebra. And the vector field corresponding to that is X hash, which I also called psi X. And X hash is given by for X equivalent to some 3 vector A. So you can ask, is this action Hamiltonian? So we have this vector. Is it a Hamiltonian vector? Well, we should work out the internal product of that vector with our symplectic 2 form. And indeed, all things do work out well. There is a mu x which does the job, and the mu x is this one. So mu the moment map that does this, that allows us to write this one form as a exterior derivative of some function, is this one here. So mu takes a point in the manifold M and hands us back y, and y is identified with this map here, wherever I wrote it, here, with an element of the dual Lie algebra like that. And the way it works is just like that. And this vector y is the momentum vector. Okay, so that's our first example of a moment map. We'll do one more to show that actually it works in the non-abelian setting as well. Okay, the last example is to do with rotations of space-time. Well, time is not really relevant here. Rotations of space. So now we're going to look at how do rotations act on phase space. So given a G, we need to find a symplectomorphism acting on M for every G. So this is, we discussed how to do that because M is the cotangent bundle of R3. And we have an action, a diffeomorphism acting on R3, which we can lift up to a symplectomorphism on this symplectic manifold here. So the group acts on R3 just by rotations. And we have this result many lectures ago that if you have a map acting via diffeomorphisms on M, then you can lift that to a map psi hash acting via symplectomorphisms on the cotangent bundle. Put the hash downstairs. And the vector field corresponding to this call it capital psi. So corresponding to any infinitesimal symplectomorphism, there's a vector field on T star M. And that vector field psi is indexed by an element of the Lie algebra. So here A is an element of the Lie algebra. So this vector field psi A is an element of the symplectomorphisms of T star R3 omega. So it means it's a vector field. And that vector field, which depends on the element of the Lie algebra, when you evaluate it at some point in this manifold, has the following formula. This is an exercise. So now these things you just interpret this as a vector in the tangent space at the point xy. And then this is Hamiltonian. And the corresponding moment map goes from R6 to R3, right? At every point in our phase space, we need an element of the Lie algebra. And it has the following formula. So when you evaluate it at xy, you get the cross product of x and y. This is a bit of it's an exercise. It took me a couple of lines to do it. I'll write it like this. X, y. And if you want to know what's the Hamiltonian corresponding to one rotation or another, then you could work that out if you want. Put in the generator of the rotation, A, and you get back the following formula. And we have a name for this map. It's called the angular momentum. So this is indeed where the moment map gets its name from, this example. The moment map is the map which gives you the momenta corresponding to these symmetry transformations of translations and rotations. All right, I think that's a good moment to close out this course for the year. We'll rejoin the course next year in early January, where we will start studying a couple of major results that people have derived in the context of symplectic geometry. There, the proof density will drop to 0, and I will rather state the theorems rather than going through the extremely lengthy and often quite ingenious arguments. And then I hope by the end of this course we'll culminate in the statement of this Dijkstermaat-Heckman theorem, which is the core goal of this course to reach. But for now, thank you very much. Merry Christmas and Happy New Year.